Welcome to Chemistry with Harshada. Let's continue the next modules. Welcome to Module 5 Cycloalkanes and the concept of ring strain. Up until now, we've looked at free-flowing, straight-chain alkanes. But what happens when you take the two ends of an alkane chain and tie them together? As the top diagram shows, you get a closed loop, a cycloalkane. However, forcing atoms into these closed shapes creates a unique problem, ring strain. Ring strain is driven by two main factors. The first is angle strain, perfectly illustrated here by cyclopropane, a 3-carbon ring. Recall from Module 2 that an sp3 hybridized carbon wants its bonds separated by an ideal tetrahedral angle of 109.5 degrees. But to form a geometric triangle, those internal angles are violently compressed to just 60 degrees. This massive angle deformation pushes the electron-rich bonds dangerously close together. As the text bluntly states, forcing angles this far away from their ideal state is a nightmare for bonds, creating a severe tension zone that makes the molecule highly unstable. The second factor is torsional strain. Remember how straight-chain alkanes could freely spin their bonds to find comfortable, staggered positions? Rings lose that luxury. The structure is locked. The ring cannot rotate freely. Because the carbons are tethered together, the hydrogen atoms on adjacent carbons are rigidly forced into those high-energy, eclipsed positions. As shown in the Newman projection on the right, these eclipsed hydrogens are permanently clashing. The molecule is trapped, unable to twist away from the intense torsional strain. Together, this forced angle compression and inescapable torsional crowding define the tense, pent-up energy inherent in closed ring molecules. Welcome to Module 6, Cyclohexane, the king of stability. In the previous module, we saw how rings can suffer from intense strain. But the 6-carbon ring, cyclohexane, is the superstar of the group. As the diagram at the top shows, it completely avoids ring strain by refusing to sit flat. Instead, it naturally bends and puckers into a three-dimensional shape known as the chair conformation. By adopting this shape, it achieves perfect tetrahedral angles and perfectly staggered bonds. It is the absolute king of stability. Within this chair conformation, the hydrogen bonds point in two distinct directions. First, we have the axial bonds, illuminated here in purple. These stick straight up and straight down from the ring, alternating position on each carbon. Next, we have the equatorial bonds, highlighted in cyan. Just like the equator of the Earth, these bonds point outward, radiating around the perimeter of the ring. Understanding these positions becomes critical when we attach larger substituent groups, like a bulky methyl group. Look at the red diagram on the left. If we force the methyl group into a vertical, axial position, it physically clashes with the other axial hydrogens on the exact same side of the ring. This fiery clash is called a 1,3 diaxial interaction. It causes severe steric crowding, resulting in a highly unstable, high-energy state. Now look at the green diagram on the right. If we place that same methyl group in an equatorial position, it points harmlessly out into empty space. It completely avoids bumping into the other atoms, resulting in minimal crowding and a low-energy, highly stable state. This brings us to the ultimate golden rule of cyclohexane rings. Larger substituents will always prefer to occupy the equatorial position to avoid those punishing 1,3 diaxial interactions. We've explored the twists, the turns, and the incredible tension of molecules. But the ultimate question remains, why does this matter? It matters because in the physical world, especially in biology and pharmacology, shape dictates function. Look at the top diagram. Here we see a synthesis product, a specially designed drug molecule, approaching a protein receptor. Because its 3D stereochemistry is perfectly aligned, it slides right in, creating a flawless stereochemical fit that triggers a biological response. Conversely, the misfit molecule beside it might have the exact same chemical formula, but because its 3D shape is wrong, it is rejected. The shape of the molecule dictates whether it fits into a receptor, or if a chemical reaction happens at all. Let's review the rules of this microscopic world. For straight-chain alkanes, their sp3 tetrahedral geometry allows for free rotation around their sigma bonds. Their stability is entirely determined by this rotation, favoring the relaxed, staggered states over the crowded, eclipsed ones. Cycloalkanes, however, face restricted rotation. Forcing them into rings introduces severe angle and torsional strain. Yet, nature finds a way, as seen in our superstar, cyclohexane, which bends into the ingenious chair conformation to perfectly minimize that strain. As we conclude our journey, remember this: these molecules are not static drawings on a page. A deep understanding of this constant, 3D dance of alkanes is the ultimate secret to engineering the next generation of molecules for biology, medicine, and materials science. Welcome to the Master Review module, Alkanes, Stereochemistry, and Conformations. Let's bring all the foundational concepts together into one definitive summary table. We begin with torsional strain. As described in the second column, this is the resistance a molecule feels when twisting around a single bond. It's caused by the electron repulsion between those overlapping, eclipsing bonds. Look at the key examples on the right. The molecule is perfectly relaxed, minimized strain in the green, staggered conformation. But when forced into the red, eclipsed state, that strain is maximized. Next is steric strain. While torsional strain is about overlapping bonds, steric strain is about physical, spatial crowding. It's the repulsion felt when atoms or bulky groups are forced too close together, specifically, beyond their natural van der Waals radii. The classic example shown on the right is the gauche interaction in butane, where those two large CH3 methyl groups are rotated just a bit too close for comfort. Moving down, we have angle strain. This is the structural penalty a molecule pays when its bond angles are forced to deviate from the ideal tetrahedral angle of 109.5 degrees. The most extreme example is cyclopropane. As shown in the diagram, tying 3 carbons into a triangle forces the internal angles down to a punishing 60 degrees, creating a massive tension zone between the atoms. Finally, we arrive at conformational analysis. This is the grand culmination of everything we've discussed. It is the active study of the energy changes that occur during the rotation around those single, sigma bonds. By combining our knowledge of torsional, steric, and angle strain, we can use tools like sawhorse drawings and Newman projections to map a molecule's exact energy state as it twists through space, perfectly charting its peaks of instability and its valleys of rest. We will see the Remming modules in next video. If you found this helpful, don't forget to like and subscribe for more deep dives into the molecular world. See you in next video. Happy learning chemistry with Harshada.